Hello all, and welcome back to ECMath. Today we're going to look at section 4.4, which I would entitle More Trig Fun. It's just kind of more problems that relate to the trig ratios, kind of in every quadrant. So we're starting to break free of the unit circle and get back to maybe some triangles, maybe some coordinate systems. See, these are just some other things you can do with the knowledge of trig that we now have. So the main prerequisite for this section is the coordinate definitions of the trig functions. And I think we actually filled this out on a previous note sheet. You had a table like this, so you may already have this, but I'm just going to go over it one more time because it never hurts to see again. So we might have a circle, and for this day, I'm going to say that we have a circle of radius r. And let's assume that we have a point on this circle, so that has coordinates x, y. Then we can make a triangle where the vertical length is y and the horizontal length is x. So we have a triangle that goes x, y, and r. And basically abstracting SOHCAHTOA trig to this situation, we can write the following definitions. And these, specifically the r, x, and y, relate to the radius of the circle and the coordinates x and y of that point. And because we're talking about coordinates, it's really vital, or it's really useful that a coordinate could possibly be negative. So like in this quadrant, all the coordinates would be positive and positive. But in this quadrant, both coordinates would be negative. And in this quadrant, the x coordinate would be negative, but the y would be positive. And in this quadrant, it would be the opposite of that. And we made kind of a nice little chart that talks about what quadrants sine and cosecant are positive in. Since it's related to the y, sine is positive in the upper quadrants and negative in the lower quadrants, and same with cosecant. Since it's related to the x, cosine is positive on the right and negative on the left. And since tangent is a ratio of both of them, you have two negatives or two positives make a positive, but when one of them's negative, the other's positive, tangent's negative. So we made that nice little chart, which we're going to use a lot today, thinking about the signs, SIGNs of the trig terms. I'd recommend you keep your version of this note sheet, whether you wrote it down or you have that sheet, in front of you throughout this video, because we're going to be using these definitions and assuming you have them pretty much at your fingertips. So, first question. I call this trig given a point. So let 7, negative 24 be a point on the terminal side of an angle theta. Evaluate all 6 trig functions of theta. So the first thing to do is try to draw out an angle theta roughly to scale. It doesn't have to be super to scale, but we need to get it at least in the right quadrant. So I'm not going to count out 7, but I'm going to say that's 7, and this is negative 24. I'm going to use that point to make a triangle. So notice I'm definitely not on the unit circle, right? These are way too big of numbers. Now technically theta could be this angle, or it could be this angle, and the problem doesn't really specify if theta has to be positive or negative, but the trig values are going to be the same for both of them because it's talking about angles with the same terminal side. So it doesn't matter which direction theta opens. It could be big, it could be small. The first thing we need to do is find r. Well, it's a triangle, so r squared is going to be x squared plus y squared. So that's, which is 576. This together is 625, which is 25 squared. So then r should be 25. So we can label that on here. You may have recognized that that's a special triangle. 7, 24, 25 is a Pythagorean triple. That is one of the special triangles that it's a little bit helpful to know in this section. We have 3, 4, 5, 5, 12, 13, 7, 24, 25. There's infinitely many more, but those are some good ones to know. So we found our r. I'll just move that up here. And now we're ready to do all the trig. We just use the coordinate definitions that we wrote before. So I don't know what theta is, but I'm still going to write sine of theta because I always need to talk about the argument. You need to have that theta there. So I'm going to write sine of theta, and we'll just look at the triangle. So opposite over hypotenuse. I find it easy to do the reciprocals along with the function that I'm doing. So cosecant of theta is taking the reciprocal and then moving the negative to the top, negative 25/24. Cosine of theta is adjacent over hypotenuse. And that makes secant theta 25/7. And tangent theta, negative 24/7, opposite over adjacent. And cotangent theta will be negative 7/24. Again, taking the reciprocal, moving the negative to the top, just for tidiness reasons. And it's done. The only thing you have to be really sure of, and I am going to be picky about this, is I need you to write that theta. Because again, we're always being sure that we know what's an input, what's an output. So get in the habit of writing that angle theta there. All right. That was example 1. That's one kind of trig tricks you can do, to do trigonometry in any quadrant when all you're given is a coordinate point. So now, let's visit again some trig functions of quadrant angles. So the quadrant angles are those angles that match with the 4 quadrants, and the issue that everyone runs into, and we've talked about this in a previous video, is that you can't make a triangle. That's not the right triangle to make. If any triangle could be made, it would have to be like a triangle where that's one leg, and that's another leg, and then the base is right here, but the base is 0, right? This does not make sense to talk about a triangle. So if we want to do trig on these angles, we need to use the coordinate definitions. So when you're doing quadrant angles, what you want to do is draw yourself out a little quadrant, a little axis, and draw yourself out a little circle, and pretend that it's a unit circle. So you get to choose the radius in this case, right? It doesn't specify what the radius has to be, so you get to pick. So let's let r equal 1, and then we can list out the coordinates. So this is 1, 0, 0, 1, negative 1, 0, and 0, negative 1. Why do I need that? Well, because as I'm going around my quadrant angles, I'm going to need to use those values. So sine, just to do part A, sine of 3 pi over 2. Sine is y over r. Well, the y is negative 1, and the r is 1. So this is negative 1 over 1, which is negative 1. So we'll write that sine of 3 pi over 2 is negative 1. These are really important angles. Like, if I think about common trig questions that we need to be able to answer quickly just throughout like all of math, sine and cosine on the quadrants, they're one of the most common trig ratios you end up evaluating. So make sure you know how to do this. You can't make a triangle, but the coordinates always work, and the answers are almost always, nice numbers. Now I said almost always because what happens when we try to compute the cotangent of pi? Okay, we need to do some definitions first. Well, remember, cotangent of theta is the reciprocal of tangent, so that would be x over y. Okay, so then the cotangent of pi would be x over y, negative 1 over 0. Uh-oh, we've divided by 0, which means that cotangent of pi is undefined. So whenever you get 1 divided by 0, that's undefined, or negative 1. It doesn't matter. There's no negative undefined. And just to clarify, of course, 1 over 0 is undefined. 0 over 1 is very much defined. It's equal to 0. So depending on the ratio you're doing, you might get 0, you might get undefined. You have to simplify it, right? You don't leave me negative 1 over 0 or 0 over 1. And I didn't write it on the page, but if I were doing, say, tangent of pi, that would be y over x, which is 0 over negative 1. I need you to simplify that to 0 so I know that you understand this. Never leave 0 over 1 and just, you got to simplify that out. So tangent of pi, by the way, is 0. The next group of problems are problems that I call quadrant clues. They're basically telling you something about an angle, but they're not going to be super direct about it. Instead, they're going to sort of rely on you to use some of the clues to figure out like what quadrant an angle might be in. So example A asks, if cosine x is less than 0 and sine x is greater than 0, what quadrant is x in? And in this case, x is an angle. Well, let's think about this. Cosine of theta is defined as x over r, and sine of theta is defined as y over r. So if cosine of x is less than 0, that means the x coordinate of a point on that angle must be negative. And if sine x is greater than 0, that means the y coordinate must be positive. So then I can just like think about which quadrants have negative x but positive y. And I think about it for a little bit, and I know y is here, negative, positive, negative. Well, I see that we would have negative x but positive y over here in quadrant 2. So angle x is in quadrant 2. And I know there's a little confusion because here I'm talking about the x coordinate and this x is talking about the angle. That sometimes happens in trig. We try to avoid it, but sometimes that is a little messy. So make sure we separate the variable x from the coordinate x. In this case, anyway, quadrant 2, not 11. That's 2. One sort of short mnemonic for doing this, a way to remember it, is to make a chart like this. So this is a chart that says which functions are positive in which quadrants. So in quadrant 1, all functions are positive. In quadrant 2, sine and its reciprocal are positive because they're both the y coordinates, right? So we have like y is positive. In quadrant 3, tangent and cotangent are positive because they're both y over x. And then when y and x are both negative, then those both become positive. And in quadrant 4, cosine and secant are positive. Sometimes this chart is abbreviated further into just the letters A, S, T, C, which I've heard stand for A smart, Trig, class. Or all students take calculus, or there's a number of different mnemonics, or you can make up your own, whatever helps you remember it the best. Personally, I don't really love that ASTC trick. I'd rather think about the coordinate definitions and work from there, but some people like different things and it helps you remember in different ways, so use this if you want, don't use it if you don't want. So let's do some more quadrant clues. This next problem says, if tangent of theta is negative 3/5 and cosine theta is positive, what quadrant is theta in? So I want to think again. Cosine theta is like the x coordinate. So if cosine theta is positive, then we better be in quadrant 1 or 2, because that's where x is positive, right? That's where x is positive. But if tangent theta is negative, well, where's tangent negative? Tangent's negative in quadrants 2 and 4. So what's the overlap of these two drawings? I guess I could just do this. And notice that the only quadrant that satisfies both of them is quadrant 4. So this must be in quadrant 4. And once I know that theta is in quadrant 4, we can draw it. So we'll get out here, draw a quadrant 4 angle. And I'm not going to try to draw anything to scale right now. I'm just going to draw, angle theta. We can mark that as in here. And we know that tangent is negative 3/5, so that means the opposite is -3 and the adjacent is 5. And like I said, I'm not even caring that I'm not to scale right now. What are the values of cosine and sine? Well, I have a triangle. All I need to do is find the missing side. In this case, we need to use a Pythagorean theorem. So this is the square root. Be careful, this is not a 3, 4, 5 triangle. And I did that to trick you. This is the square root of 5 squared plus 3 squared, which is the square root of 34. Hypotenuses are always positive, so the only negative here is the 3. And then if we want to answer the rest of the question, we can say that cosine theta is the adjacent over the hypotenuse, so 5 over square root 34, and sine theta is the opposite over the hypotenuse. But because we're in quadrant 4, we use the negative length there over root 34. And you know, in the past I've said to rationalize your values. I really like it when you rationalize standard root values like root 2 over 2. I think that should be rationalized. 5 over root 34, I'm fine with that. Because if you rationalize it by multiplying, by doing this over that, you get 5 root 34 over 34. That's not like particularly simpler. I think I'd actually prefer the other value. You can rationalize it if you want. If you're checking your answers in the back of the book probably rationalizes it. But the decimal equivalents are the same. Not that you should give the decimal, but they are the same number. So in a problem like this, where nothing simplifies, I don't actually care if you rationalize. And I think that these values are perfectly fine. And I would say probably like an important part of your answer and showing your work is that sketch of the triangle. So make sure that like all of those are included as well when you do problems like this. So the next trig thing to look at is something called reference angles. We've actually been using reference angles for a couple days now, but we haven't really formalized it. So here we go. A reference angle is an acute positive angle that's made from the terminal side of an angle to the x-axis. And I have 4 little quadrants here because the reference angles kind of look different in each quadrant. So I want to give you a diagram of like what a reference angle looks like in each of the 4 main quadrants. So we're going to start with quadrant 1. It's kind of trivial, but say we have an angle with a terminal side in quadrant 1 like that. And maybe we have an angle like bigger than 2 pi. You know, maybe we have an angle like 7 pi over 3, right? 1 more than 6 pi over 3. Then the reference angle is the angle made when you drop an altitude down to the x-axis and just look at that triangle. So acute positive angle, well, 7 pi over 3 is not acute, but what is acute is pi over 3, right? So you're basically subtracting 2 pi. So in this case, it's like theta minus 2 pi. Was how we found that reference angle. So we're going back to the 0 axis there. Now, what if our reference angle was in quadrant 2? So maybe it would look like this. And maybe theta would be 5 pi over 6. Well, we would drop an altitude to the x-axis, and the reference angle would be this angle right here. Well, in this case, we're looking for how far we have to go to get to pi. So I would do pi minus 5 pi over 6, which gives me a reference angle of pi over 6. So reference angle in this case is the smaller angle, pi over 6, and generally you can do, in quadrant 2, you can do pi minus theta. What if we're in quadrant 3? So what if my angle theta was 4 pi over 3? You might be tempted, a lot of people try this, to say, oh, well, the smallest angle towards the closest axis is down here as a pi over 6. However, you have, if you've done that, you've broken the key rule, which is that we always make our reference triangles with the x axis. And the reason we do that is that it helps us keep our opposites and our adjacents straight. If I start making reference triangles with the wrong axis, we're going to get sine and cosine mixed up. So instead, the reference angle is actually going back to the x-axis, and when we make our little triangle, our trig triangle like we're used to, that's the triangle we're trying to make. Actually got to zoom in here. Get rid of that. So in this case then, I would do 4 pi over 3 minus pi, because pi is the smaller of the two angles, which gives me 1 pi over 3 as the reference angle. And I guess generally, in quadrant 3, you would do theta minus pi to get the reference angle. And what if we're in quadrant 4? So in quadrant 4, we have an angle that is, straight out in quadrant 4, something like this. So that would be 7 pi over 4. Well, in quadrant 4, we're going to drop our altitude from the x-axis down to make our triangle. Again, always going to or from the x-axis. And the reference angle is this acute angle here, 7 pi over 4. To get up to 2 pi, we need 1 more pi over 4. So that's the reference angle. And I guess a formula, if you need it, to calculate reference angles in this quadrant would be maybe 2 pi minus theta would give you the reference angle. I'm not being super formal about these formulas because you'll notice that in every quadrant there's a different formula. I don't think you should use a formula at all. I think you should draw a sketch. The picture is what tells you what to do. And you should always be thinking about triangles and angles geometrically. This is not an algebra section. This is a geometry section, and you've got to make those drawings. So why the heck do we care about reference angles? Well, if you notice in all the examples, the reference angles were some of our most critical trig angles, right? Pi over 4, pi over 3, pi over 6. Those are the ones we have memorized. We know those angles. And that brings us to the key fact about reference angles. A trig function of a big angle, like 7 pi over 3, has the exact same value as the trig function of its reference angle. Except that the value of the larger angle might be negative depending on the quadrant and function. Again, using that this shorthand or thinking about the coordinate definition. But the values will be the same because, for example, to zoom in on this triangle, all I've done is take a 30, 60, 90 triangle and flip it over into the third quadrant. No lengths have changed there. The only thing that's changed is whether the sides are positive or negative because they're going now in the wrong direction. So that's the key value of reference angles. And we just have a couple more problems to do that involve them. So let me show you how to do some of these. Actually, I'm going back to this picture because the main use of reference angles is just to do normal trig. So for example, if I ask sine of 5 pi over 6, well, that's basically saying make a reference triangle in the second quadrant, and sine of 5 pi over 6 is going to be the same as the sine of pi over 6 because those triangles are just reflections of each other and they have the same opposite side in the same direction, up. And so if you've been calculating trig using triangles, which is how I think you should do it instead of memorizing, you've already been using reference triangles a whole lot. But there's some other applications too. So let's look at this problem. Given sine of 20 degrees, we'll be in degrees for a minute, is 0.342. There's no way to memorize this. You'd have to be given that value if you weren't having a calculator. And then you say, how do I find sine of 160 or sine of 200? Well, like we said before, the best move is to make a sketch. So 20 degrees is like here. And they're basically saying that if the hypotenuse is 1, this length is 0.342. That's what the first piece is saying. Now we're looking at 160 degrees. Well, critically, 160 degrees is exactly 20 degrees away from the x-axis. So if you make a reference triangle here, notice that those triangles are exactly mirrored, which means the y value is still going to be 0.342. And the hypotenuse will still be 1. So if you know sine of 20, because they share a reference angle of 20 degrees, sine of 160 is also 0.342. No calculator needed. And let's see if we can find the sine of 200. Well, I know that this is 180 degrees, so 200 would be 20 degrees more. So I'm again looking at a reference angle of 20 degrees. Well, all of these triangles are congruent. They've just been reflected into different quadrants. However, when I label these sides, it's going to have a value of 0.342, but it's pointing downwards now. So that's negative 0.342. And the hypotenuse is still 1, which means that the sine of 200 is the opposite of the sine of 20. So the sine of 200 is negative 0.342. Given all this information, given one piece of information, you can actually find the sine of a bunch of different angles just because of sort of the symmetry of the circle. I'll leave it as an exercise to you to think about what is the fourth angle that you could now find the sine of, knowing everything we know here. And the last thing we're going to do today is use reference angles to think about which trig functions are equal without finding the values. I know that you could just do this by calculating every decimal there, but the goal here is to actually think instead of just calculate. So that's what we're going to do here. So the question is, which of these are true? If false, fix them without just changing the angles or functions to something completely different. So we're going to go one by one. First is about pi over 3 and 4 pi over 3, and also about tangent. So we're going to kind of use everything we learned from this section. So the first thing that we're going to do is draw the angles. So pi over 3 is up here, and 4 pi over 3, that's down here in this quadrant. And I notice that pi over 3 has a reference angle of pi over 3, but 4 pi over 3 also has a reference angle of pi over 3. I also know that tangent is positive, negative, positive, negative, so the tangent function would have the same sign in both quadrants. So since they have the same reference angle and the tangent function shares the same sign in both quadrants, this statement must be true. They're symmetric triangles and the function's the same sign. Part B, tangent of pi over 3 is equal to tangent of 5 pi over 3. Okay. This is similar to the last one, but they've changed the second angle. So let's sketch those out. Now 5 pi over 3 is down here. And you might think that this is also true, just like the first one was, but be careful. They do both have a reference angle of pi over 3, right? They're symmetric in that way. But remember that the tangent function goes positive, negative, positive, negative. So tangent of 5 pi over 3, that should give you a negative value. But tangent of pi over 3 should give you a positive value. Well, you can't have a negative value equal a positive value. So as written, that has to be false. I'll just do F instead of writing false. But we could fix it pretty easily. Because right now, we can see from the picture that they have the same size. They're just in the wrong direction. So all you have to do to fix this is make one of them negative. I'm going to make the first one negative. But it doesn't matter which one. A lot of people think that, like, because that's a negative value, you have to put the negative sign on that one, but that's not actually true. The negative that I'm writing here basically means, it doesn't mean it's a negative number, it means opposite, which is, a really good way to interpret a negative sign multiplied to something. So what I'm saying is the opposite of the tangent of pi over 3 is the same as the tangent of 5 pi over 3. And that would be a true statement, because they have same value but opposite signs. All right, so C, we have cosine 5 pi over 6 is the opposite. So again, I'm going to read this as opposite of the cosine of 11 pi over 6. Well, we better sketch all those angles out. Let's sketch that right here. So 5 pi over 6 is in this quadrant, and 11 pi over 6 is over here in that quadrant. In blue. Now the cosine value, we'll make the triangle, but the cosine value is the x-coordinate, here and here. And I notice that they're symmetric triangles, but they're opposite signs. For 11 pi over 6, the x value is positive, but for 5 pi over 6, the x value is negative, so they'll be the same but opposite. Well, that's what this says, right? They're the same but opposite, so this statement is true. And again, we've done this without computing anything. Like, yeah, we know that cosine 5 pi over 6, if you think about it for a second, is square root of 3 over 2. And you could compute the other one and do it that way, but that's not the goal here. The goal is just to use symmetry to avoid doing calculations. We love avoiding calculations. All right, so let's do some pi over 4s. Last one. So we have 5 pi over 4, which is 1, 2, 3, 4. 5 pi over 4 is over here. And 9 pi over 4, well, that's like 8 pi over 4 plus pi over 4. So that's actually in the first quadrant. Greater than 2 pi. And the question is, are the sines equal? Well, sine is the y-coordinate of a point on that angle. So we can observe that although they do have the same reference angle of pi over 4, right, that little reference angle is both pi over 4 in both cases. For 5 pi over 4, that side would be negative, but for 9 pi over 4, that side would be positive. So, as written, this statement is false because they have opposite signs, even though they're talking about the same triangle. But it's an easy fix. We could just write that the sine of 5 pi over 4 is the opposite of the sine of 9 pi over 4. And that would be our corrected statement here. And again, basically this explanation is the drawing. Here's all those all together if you need to get any of them down. So it was true, false, and we fixed two equations to be correct. All right, folks, thanks for watching this video. That is the last trig trick. The next thing to do is just put everything into practice that we've learned. I know that there's a lot to know with trig. There's all these coordinate definitions. There's all this stuff with quadrants. Just draw a lot of pictures. It really helps. Get used to making triangles and practice your radians every day. Have a good night, folks. I'll see you all in class. Thanks for watching.